So the first question is asking us about K-nearest neighbor, and this is a classification problem. And we're saying we have this data that is labeled with two classes, the red and the blue. And we have this new point that we want to classify. So this green point is a point that we don't know what label it is, and we want to predict whether it is a red or blue one. And with K-nearest neighbor, the algorithm is simple. We look at the nearest neighbors of the point that we want to predict. We make a vote and we decide. So if K is equal to 3, we're looking at these 3 points, and the vote would be that this one is predicted to be red. If K is equal to 5, now we're looking at these 5 nearest neighbors, and the vote will be blue, and the prediction for this point would be blue. Now, before we answer this question, how do we actually calculate the nearest neighbors? Like, how do we find those points if you're writing the algorithm for it?
If I recall correctly, you have to establish how many neighbors you want to find and all that there. So you have to establish what your K is equal to and all that there. So if we have like K is equal to 3, that means that given a point, we have to find the 3 neighbors, you could say, that are closest to that given point and all that there. And I'm not sure, but does the threshold really matter, or is it really just like whichever 3 are closest, that's your threshold?
There's no threshold. It's more like the 3 closest ones if K equal to 3.
Right.
But how do you find which ones are the closest? Like those 3, how do you find them? Because visually it's easy, but and in your program, how would you find them?
You have to compare the distance between virtually all points, I would think.
And in order to do that, you need to go through all the data that is present and then find from the starting point the 3 nearest neighbors, or the 5.
So yeah, you'll have to calculate the distance from this point that you want to predict to every point that you have in the data, and then like probably sort them and get the 3 nearest ones. So distance here, like there's many measures for distance. I think the one that you guys know is the Euclidean distance. So that's popular and it's used a lot, but there's also other measures for distance. When we're dealing with big data, distance kind of stops working, especially the Euclidean distance. So by big data, I mean higher dimensions, not necessarily a lot of points, but higher dimensions of data. So if like right now we have 2 dimensions only, but if you have like 1,000 dimensions in your data, it would actually be interesting if you want to just generate random 1,000 points, like points with 1,000 dimensions, and calculate the distances between them, and you'll see that almost all of them becomes almost the same distance from each other, because distance kind of stops working at high dimensions. It's known as the curse of high dimensionality. So there are other like distance measures that are usually used with high dimensions, especially in a big data application, because big data here can mean a lot of data, but can also mean many dimensions. We're not going to be looking into them, but I just wanted you to like know that distance, there's many metrics for distance. In fact, you can define your own metric for distance. It has to like follow some rules that like the distance from A to B should be equal from the distance from B to A, and the distance from A to A should be equal to 0, and things like that. And like the distance from, anyway, so I think there were 3 rules to define any measure, like a distance measure. So yeah, you have to calculate the distance from this point that you want to predict to all the points that you have in your data set to be able to find the nearest ones. And then you can make your decision. So obviously this algorithm isn't, I would say, efficient for big data, probably, meaning that you still, for every single point, you have to calculate for all of them. Now, having said that, yes, Tristan.
I'm just thinking about it right now. Like, wouldn't it be like a lot of Pythagoras calculations, more or less, or really just differencing? If you have your points put in a Cartesian plane, and then at that point it would just be like doing a lot of subtraction calculations to find the difference and all that there.
Well, I mean, you're thinking of it as a graph that you're looking at.
Mhm.
But when you're thinking of it as just x, y, just two numbers, x and y for every point, sure, there's a Cartesian plane, but you're not necessarily looking at it. You're not seeing it, and when you're calculating the distances, it does follow that visual thing that you're talking about. But you have to still apply it to every single point. You cannot like say that it is around this circle because I see those points now. You don't have a visualization of it or a plane or something. I don't know if that answers your question.
Well, because the fact that you don't have a way to visualize it, it would be different by nature then?
No, it's not about different, like the way to, do you know what Euclidean distance is?
Yeah, more or less and all that there. Yeah, that's
Which is like maybe abstracted from what you're saying, like the Pythagoras theorem and all of that, right? But this is the formula. Like if you're trying to find distance from point P to point Q, the square of it is equal to this. So the Q1 in this case is like the X value of Q, and Q2 is the Y value of Q, and P for the same thing. So it's Q1 minus P1 squared plus Q2 minus P2 squared. And the distance is the square root of all of this. Usually when you are doing something like K-nearest neighbor, you don't care too much about the exact distance, you care about the comparison. So you even don't usually calculate that square root, like you keep it squared. So you only deal with this part, because whether it's squared or square rooted, it will, when you're comparing two of them, this will still be bigger than this, whether you're taking the squares or the square root of the squares. Did that make sense, or did it confuse you more?
No, yeah, I get it.
Yeah, so this is a distance that you're calculating. So even in like if you have 1,000 dimensions, this still applies. It will be like Q3 minus P3 squared and so on, plus, and you keep adding the dimensions you have. And this is called the Euclidean distance. You have other distance, like the Manhattan distance, for example, for binary data. I think the Manhattan is the one for, actually, no, sorry, not the one for the binary, but the Manhattan distance is about the difference in the points. So if you have like 2 points, x1, x and y, so x1 and actually 0.1 and 0.2, and you have x1 and y1 for every one, and x2 and y2 for the second point, and if you're calculating its distance, it's basically just the difference between the x's plus the difference between the y's with like the absolute of them to remove the negative stuff. And that's called the Manhattan distance. So that's another like distance measure that is widely used also. The one that is usually used with big data is the cosine distance or cosine similarity. And this is a bit more complex, but this is usually used more with higher dimensions than Euclidean distance. But anyway, so now the question is, what do you think is better to use, a large K value or a small K value? And whenever you get such question, like you should be analyzing. Don't just give it a number like K, like yeah, large or small. What would affect the prediction? I would say, how would a large K value or a small K value affect the prediction? And you can start thinking from the maximum, like take a very big K value and a very small K value. How do you think would actually make a difference on the prediction? Anyone? Okay, Jonathan is saying small k value is more precise. Okay, let's say k is equal to 1. So you're saying small k value is more precise. Let's say k is equal to 1. Would that be more precise?
Technically it's not more precise, because like k equal 1 is like the first element that's near the point we're comparing to. Like the main difference between a small and a large is more like on the number of elements that comes into account when we're comparing to. And like if that number of elements that are different have like different pull different way or not, like if they pull the same way, then using a large or a small one doesn't necessarily change anything. But let's say like in our case here, where a small one pulls toward the red, where a big one pulls toward the blue, then like have using different size of k value like gives more different lookout on the elements that are present.
If we have let's say 1,000 points, like our data set consists of 1,000 elements, and k is 1,000. What does that mean for every point that we are trying to predict?
If we have 1,000 pen and we have a k of 1,000, it's basically we're comparing the point against the whole data set.
So the whole data set now is making the decision of what this point belongs to. In other words, whatever class has the more points, that's the dominating point. That's the dominating class.
Yep.
So it stops being related to this specific point. Now it's just about of like, do we have more reds or more blues in the data set, and that's it.
Mm-hmm.
So the bigger k is, the more you're going out of like, does it actually matter what this point is with the neighbors that correlate with, and now like how many points we have in the space within that you're looking at. And if you go very small, what if there's a point here like very close to it that is red and everything around it is blue, but this point is like an outlier? Now you're making a decision based on possibly an outlier, like just one value. So neither is good. Like very, very small is not good, and very large is not good as well. Now we have a good command. If the points are generally close to each other, then k that is smaller is better. That is a good command. That it can be determined based on also like the variance between the points, how spread the points are from each other, can help us understand like what would be a good k, because you basically want to find a k that does not bias the solution based on like the points that we have, the number of points we have, but also has enough information to make a decision. And the short answer is that it's usually like kind of a trial and error, where you start somewhere and you test different Ks and you compare the results on actual testing data that you would have, and you find the proper K for your data. But it's good to understand the effect of like a large K and a small K on the actual prediction. Okay, any question about K-nearest neighbor? Okay, now the second question is about when we're dealing with a binary classifier like SVM, the classifier can only classify two classes, like right and left, or red and blue. But if we have a data set with 1,000 classes in this case, as an example, and we want to use a binary classifier like SVM, we can use strategies like one versus rest or one versus one to be able to classify the data on 1,000 classes using a binary classifier by simply creating multiple binary classifiers. Instead of having one classifier, we'll be dealing with multiple. So the question is saying that we have 1,000 classes, and which method would be better in this case, the one versus rest or the one versus one? Who can give us an answer? Okay, if you write none on the test, you get a 0, because it doesn't matter if it's none or this or that if you cannot
Explain it.
Jonathan, you also get a 0 if you write 1 versus 1.
Well,
You have
like,
to analyze the both to, and then give your kind of analysis, like what you would suggest. But what you suggest might not be a perfect answer. But from the analysis, whoever is dealing in this case, because there's also a lot of variables we don't know. How many data points per class? What is this data? How many dimensions it is? There's so many variables that we don't necessarily know to make like a 100% accurate or good judgment, like intelligent judgment. But you need to analyze it, and then you can give your opinion saying none and why it's none, and what would you suggest in this case. So if we look at 1 versus rest, we're saying that we're going to create a classifier for every class we have, in which we classify this class on one side and all the rest of the data on the other side. So if we have 1,000 classes and we have like 100 points per class, then we're dealing with like 100 points on one side for class 1, and the rest will be, I don't know, 99,000 points or something like that. Yeah, I think 99,000 points. So 100 versus 99,000 for one classifier, and we're having 1,000 classifiers of those. What kind of problem do we have here? When you have a classifier where it's classifying based on 100 points on one side and 99,000 on the other side. We have an imbalanced data set. Like chances are the classifier will be biased towards the 99,000 points instead of the 100. So whatever you pass to it, it will probably look at it as one of those, like to be classified as part of the 99,000 points, because there's so many of them, and chances are it will correlate whatever point you give it with those points. And that's a problem in which we call it imbalanced data set. And that will result, if we use 1 versus rest, it will most probably result in completely inaccurate results and inaccurate predictions. So for 1 versus rest, you maybe can make a judgment saying that because of this problem and because it will be a huge imbalanced data set problem, it will result in inaccurate results, and therefore you shouldn't use 1 versus rest. But that doesn't mean you should use 1 versus 1. So when you're looking at 1 versus 1, we're saying for every like distinct 2 classes, we're going to create a classifier for it, which means that the number of classifiers we're going to have is the combination of classes. So it's k times k minus 1 over 2. And in that case, if we have 1,000 classes, that will result in around 500,000 classifiers. So now on big data, like like with Spark, on clusters, it is doable. Like it's not impossible. So that really doesn't give you a clear answer whether you want to do that or not, but it's important to explain it and justify your explanation. Like 500,000 classifiers is still a very big number. It is doable because we have the tools for it, but is it worth the cost? I don't know. It depends on who's doing it. But you can suggest that, well, like for this problem, I will probably not use a binary classifier and just go with a classifier that is not binary. So it would allow for the 1,000 classes to be part of the model itself. Any questions about this? Okay. Now we have this neural network. It has weights, and we're saying that the input is 5.2. Calculate the output. So who have problems calculating the output for this one? So looking at this input 5 and 2. So we'll start with this hidden layer, the first node. So we have 5 times 0.1, that's 0.5, plus 2 times 0.2, that's 0.4. Why can't I? 2 times 0.2, so that's 0.4, plus the 0.5 coming from here, that's 0.9. So we'll end up here with 0.9. For this one, we have 5 times 0.4. And we have plus 2 times 0.1, which is 0.2. So we end up with 2.2. So 0.9 and 2.2. Now 0.9 times the 0.2, 0.18, and the 2.2 times 0.5, that's 1.1. And we get 1.28. I'm not sure if I did anything wrong. Did you guys get this number?
Yeah, that's it.
Okay, so my calculations are correct. So that's how you calculate this. So the answer at the output will be 1.28. Now I might give you like a problem in which you have more than one hidden layer. So you have like 2 hidden layers here, which the calculations will still be the same. You're just going to do it for 1 extra layer. So you'll evaluate the nodes here at this layer, similar to how we've evaluated all the nodes, just by the links to them and the weights. You calculate them until you reach at the end the output. Okay. Now for this question, we have k-means clustering, and we're saying we have this data, and we're using k equal to 2, and we're specifying we're using the Euclidean distance, and we're starting our centers of the clusters at point A and B, and we're saying do all the perform all the iterations to find the final, or like to find the clusters, the centers of the clusters for the 2 clusters that we're saying we're starting with. With k-means clustering, we have to specify k, which is the number of clusters that we want to find. That's something that we have to specify from the beginning. It's not going to be done by the algorithm itself. So I think most of you did not have any problem with this, but I'm going to do it anyway. So we're starting with, we have x and y, 1, 1, that's A, 2, 1, 4, 3, and 5, 4. For the test, it's okay for me if you solve it by drawing like an XY axis, like I'm gonna do now, and doing the like just observing by drawing it to scale. This would be the X, this would be the Y, or like somehow to scale. You don't have to like calculate distances exactly. So A would be here, 1, 1, 2, 1 would be here, 4, 3 is somewhere here, and 5, 4 is somewhere here. So these are the 4 points that we have. And we're saying we're starting A to be the center of the first cluster. Let's say it's the red cluster, and B is the center of the green cluster. So now the first step is to find for each point which cluster it belongs to based on the centers we have. So A, which cluster does it belong to? No one knows which cluster A belongs to?
The red one.
The red one, because it is the center of its own cluster. So it is the nearest to this cluster. So A belongs to the red one. How about B?
The green one.
Okay, C and D. Are they closest to? Are they closest to this center or to this center? They are closest to the green one. Therefore, they belong to the green cluster. Now, as long as we join new points to a cluster or remove points from a cluster, it means that we need to recalculate the centers. So obviously, looking at this, like the center right here, does not correlate with this cluster. Like it's not the center of this cluster for sure. The center will be somewhere around here. So we need to recalculate the centers. And for the green center, we have these three numbers. So the center would be 9, 11. So 11 out of 3. It's basically the average at every dimension. So in this case, X, the average of it. And Y would be, the Y would be 8 out of 3. So this is around 3.7, and this is around 2.7. So looking at it on the graph, it's 3.7 with 2.7, somewhere around here. So this is the new center of our cluster. Now, as for the red cluster, do we need to change anything?
Well, now we redo the points, right? We recalculate which side.
Yeah,
is which.
but we calculated the center of the green cluster. Do we need to recalculate the center of the red cluster?
Oh, no.
No, because it only included 1 point, and that's it. It did not change. So now, like you're saying, we need to reevaluate for each point, which cluster does it belong to based on our new centers. So C and D are still closer to the green center. So they are going to stay in the green center. However, B is now closer to the red cluster, like the center of the red cluster instead of the green one. This is closer to the red versus the green. Therefore, this is going to join the red cluster. Now, are the centers good at this point?
No.
As long as we change the points in a cluster, we need to recalculate the centers. So now the centers become, for the red ones, it's these two, A and B. So we're looking at 3/2, which is 1.5, and 2/2, which is 1. So 1.5 and 2, 1.5 and 1, it is here, which makes total sense to be the center. And then we have these C and D now, which is 9/2, which is 4.5, and 7/2, which is 3.5. So for 4.5 and 3.5, it is somewhere around here, which also makes total sense. So these are our old centers. Now you still need to reevaluate the points. Do they change?
No.
No, and therefore we're done. Like we found the centers for our clusters, and here they are. And like the answer to this question would be like the red center would be 1.5 and 1, and the green one would be 4.5 and 3.5. Those would be the new centers of our two clusters. Not the new, but like these would be the actual centers of the two clusters that we found. If K was equal to 3, we would have got completely different results. And it can depend on which points you start with. That can lead to different, like what is cluster 1 and what is cluster 2 and so on. Because with clusters, you don't have like classes, like this is a cat, this is a dog. We don't have that. Every cluster is equally the same as every other cluster, based on like just the name of it, whether it's 1 or 2 or whatever. Any questions about K-means clustering?
I have a question.
Yeah.
I wanted to know if, let's say we see, because let's say in this example, A, B, and C, like the answer was sort of obvious. Do we still need to show that we calculate the centers, or can we just, sort of assume and put, let's say, X here and whatever, and then like just draw our lines? As in like, I mean, like you calculated the average. I know for like larger scale projects, maybe it would be necessary, but since it was sort of like visual, could we do it just visually? Or do you
So
want us to
it depends
calculate?
on what I ask you. If I ask you to give me
Yeah.
the centers, like the coordinates of the centers, X and Y, then you'll have to calculate them. If I tell me with every cluster which points like belongs to each cluster, then you can do it in any way you want. Your answer would be A and B for one cluster and C and D another cluster.
Oh, okay. Also, for if you change the value of k, then you're saying that it would take, let's say, actually I was confused when you towards the end you put up the k. If you change the value of k, would it change here?
Well, K is the number of clusters we have. So
Okay.
if we were starting this, I don't know why things froze here. Okay, you can see my iPad.
Yep.
Yeah. So if we started this problem with k equal to 3, meaning that we have three clusters, and I told you that the centers of the 3 clusters starting A and B and D, for example, because K represents how many clusters we have. So you'll always need to have 3 clusters in this case. So these are the 3 centers. And you would evaluate C. C would be as part of the purple cluster. A and B will still each be a separate cluster. So this was the center of the purple. Now, after the evaluation, it will become here in the middle between C and D. Do you do anything else now?
No, I guess that would be the answer.
No, yeah, because this would be it. A would be the red cluster, B would be the green, and those would be the purple. However, if I do something like, if I give you a different input, so let's say C is this, and so if these are the 3 clusters, centers for the clusters, and now we want to evaluate them, let's look at it. So we have the 3 centers. Now A will belong to the red one. And now if we reevaluate the centers, this would be the center of this cluster. And this is already the center, and this one is already the center. And we're done. But now we got different results. A and B now are part of one cluster, and C and D are part of like one cluster each. So we got different results of clustering. And that's fine, but this happens based on your initial values that you start with as centers.
Okay, thank you.
Now, this is obviously like some, this can lead you to saying that 3 is not a good number for clusters. Because when you're dealing with k-means, usually you're doing some analysis also to find the good k. So we will actually do it in the lab and like in the exercise in which we will run k-means k-mean clustering on different k values, and then we will do some analysis to decide on the number of k's that we like number of clusters and data that we will be using. Tristan, did you have a question? Okay, I think not. Okay. So going back to the problems, now this problem is telling us that 2 algorithms were used here, dbScan and k-means clustering. Each column is representing one algorithm being applied, and each row is a data set different than the other. So who can tell me which one of these is k-means clustering and which one is dbScan and why?
If I'm not mistaken, I believe the entire left column is k-means. It's simply because of the fact that a lot of the shapes, you see like there's an even split between like with like a very that shows like different groups and all that there. But when it counters like say a more circular or irregular shape, you could say, then at that point it shows an inaccurate separation for those groups, Whereas when it comes to the DB scan on the other side, it does that much better.
Yeah, so k-means tend to like split the space into partitions, because we saw it's all about centers, and anything around that center closer to it will be part of it. So when you're seeing something like this, that's usually like an indication that k-means is probably used. Whether like also this, like it's split in half, the space. It does not detect irregular shapes like this. So yeah, everything here is indicating that this is k-means. Now for DB scan, this is also like how DB scan works. It will start with a random point, try to find all the neighbors, like the closest to it based on a threshold and the number of minimum neighbors it has. And once it's done, it can move to another random point and start finding everything. So it can detect such shapes. And one other indicator of DB scan, you can see that because DB scan can detect outliers. So if a point does not meet the minimum requirements for the number of neighbors it has within the threshold, it will be indicated as outlier. And you can see them here in the black dots and here in the black dots. Timothy, you have a question? Yes, no? Or Jordan, I see your hand also.
Oh, sorry, I was muted on my mic. The fifth one on the left column, I'm not sure.
This one?
Why is it? Why is it considered the k-means?
Well, by itself, you probably can't tell, but in the question, it says that this whole column using one algorithm, and this whole column is using one algorithm.
Yeah, sure. It's like we can deduct, but is there any indication why, or it's just like if other ones are k-means?
From these two, like looking at them, they gave you exactly the same result.
Mm-hmm.
So probably
you can't tell. Okay.
No.
Just wanted to be sure. Maybe there was some indication, but if not, okay. Thank you.
No, just visually looking at it, they have the same exact results.
Yeah.
Although you see like the order is different, but that's how it is with clustering. There is no real order, whether cluster 0 or cluster 1, they are both separate clusters, and that's what matters.
Right. Thank you.
Jordan, did you have a question?
No, it's okay. Thank you.
Okay. So moving on to the linear regression problem. So we have the following 5 observations. They are like X and Y, and we want to be able to like fit the a linear regression line between X and Y. So given X, we want to predict Y basically. And we can do the calculations easily. So let me pull up the video and the calculation for it, the formula. What happened? Okay, so that's the formula for it. So we can find for the linear equation, we'll have the intercept and we'll have the coefficient, which is the slope of the line. And I'm going to do this in Excel just to show you that like it doesn't have to be a program or anything. You can just calculate the numbers. So here I have all the X and Y's. And what I'm saying here, like to calculate B1 first, we'll need for every X that we have minus the average of X's multiplied by every Y we have minus the average of Y, and all of that summed up. So let's calculate this for every point that we have. So let's start with the mean of X. They will all be having the same mean basically. So it's the average of all the X's. If I move this like this, do you think it will work? How can I make it not move it? Do you guys know?
You have to anchor it.
Yeah, so you know how to do this?
And dollar signs, yeah.
Okay. Okay, and I'll also need the mean of the Y. So Now we're saying for every x and for every point x and y, we're gonna subtract the mean from it, and we're going to multiply those. So let's say this is xi minus mean, and this is yi minus mean. So it will be the x minus its mean, and we can do this for all of them. And this is the same thing, so it is the y minus the mean, and we can do this for all of them. And now if we want to multiply them, so we're just going to call this multiply. So it's the multiplication of this times this. And now we have all the numbers we want from the top part of the fraction, and we'll need to sum them together. So the sum of them would be minus 30. And now we want to calculate the bottom part of the fraction. It's xi minus mean of x squared and summed for all the x's. So xi minus mean squared. Which will basically be this multiplied by itself will get us the square. And we do that for all of the x's we have, and then we sum them up. And we have the bottom part of the fraction to be 40. So now to calculate b1, we only have to take minus 30 divided by 40. So minus 30 divided by this one here. And the slope is minus 0.75. So that's the slope of our line, the coefficient of b1. So now to calculate b0, what we need is the mean of y minus the b1 that we just calculated times the mean of x. So the mean of y, we can get it from any of these points, minus b1 multiplied by mean of x. So it is this one. And that's the b0 intercept. So that's the regression line for these points that we have. We can probably plot this if you want. Six, 8, 10. And we have 7, 5, 4, 2, 1. So if I'm plotting the points, so these are our points. And let's plot the let's plot the points for the line as well. So here we can calculate the line. It's basically going to be 8.3 plus the x value times the b1. So that's the predicted value. This is the actual value, and this is the predicted value. Why do we get, oh. No, this shouldn't be, the G then should be. Okay. I haven't done any plotting in Excel for a long time, so this is definitely not the way I want to do it. I want this line to be a line and this one to be a scatter plot. Anyone have an idea how to do this?
No idea.
Isn't that you have to format the graph itself?
Well, yeah, but this will change the whole thing. So these are the two lines I have, but they're not showing as points for the first one. Ludwig, do you have a suggestion?
No, I was just gonna ask, where did you get the 6.8, 5.3 from?
Yeah, so these are the predicted lines. So we found for our linear line, or like the line equation, we found the B0 and B1.
Yeah.
So given X, we can just take B0, like the equation for the line is B0 plus X times B1.
Oh, okay.
So for every point I have, I just calculated the predicted one, which is this orange straight line, and the blue ones, like the points at the blue ones, are the actual data it is. So it does fit the data kind of well. I would say it's a good fit for the data. Anyway, let's ignore the coding in Excel and move to our Python world. Okay, so any questions about this?
I guess I'll have to rewatch the videos a few times.
Yeah, I will upload this video.